in a gas mixture. The third situation would be for a pure liquid, actually, or pure solid. And the last situation is for component in a solution. That's covering absolutely everything. So we have no other types of situations that we need to concern ourselves with. So let's consider then getting going with this. And the first issue then is going to be the acidity of a pure gas. Let's let it be pure gas I. Well, I can write down the expression RT log of Fi over P. That's, of course, identically equal to what we've defined here as RT log of the fugacity coefficient for component I. And that is equal to the difference of the chemical potential here of pure component minus the fugacity here of the pure component in the ideal gas state. Continue to write this. I'll go back to the notation, putting this back in terms of G's. So we might recognize what that is. That is the departure of the molar gives free energy. So molar departure, here delta G. Well, let's drop the I for the moment. It's a pure component, so we don't need to label it. So we drop the I, and now let's write out delta G departure in some state is going to be expressible as delta H of the departure in that state minus T delta S departure, and we're familiar with both those guys. So we should be able to write them out in terms of an equation of state. And we have done that, so just harvesting that from our previous work, this is going to be recalling the integral from 0 to P of B minus T times partial B with respect to T at constant P. dP. Okay, that's my delta H departure, and for the entropy, I'll have minus T times the integral again from 0 to P. You can look back in your notes and find this expression. For that. Well, I've got integrals here in both of these terms. They're both integrated with respect to the same variable, namely dP, and they have the same limits, so I can combine them without any problem. And you notice I have some cancellation here. So if I put these together, I've got a T times this dV dt over here. That's going to cancel with that one, and what I end up with is V minus T over P dP. So there I have it. That's my molar Gibbs free energy departure, which I've now got directly related to the fugacity. So I can go ahead and take care of this if I have an appropriate equation of state that I can plug in for that. And of course, our friend, the one volume explicit equation of state that we have, which this expression calls for is our Pitzer equation. And that tells us that V is equal to so when I plug in for that, I see I just have B involved there. This is going to end up being just B times P, and remember that's RT logarithm of F over P. So I end up with my first result here, that the fugacity of a pure Pitzer gas can be written as P times exponential of BP over RT.
The P that you have in the denominator, I just want to clarify, does that represent the system pressure of an ideal gas, the reference state? Or?
No, that's the actual system pressure.
Okay. So that's the coefficient.
Ideal gas's pressure goes to 0. So P is my actual pressure.
Okay, so P at the bottom is the actual system pressure, not necessarily an ideal pressure, and
P is just the pressure of the system.
And that ratio is the what's it called, the fugacity coefficient?
Well, yeah, F over P is the fugacity coefficient, so the ratio is exponential of BP over RT.
Yeah, I just wanted to make sure there were the ratio is the fugacity coefficient inside there, and the okay,
Yep.
all right. That's what I wanted to.
So we got our first result here, which is kind of interesting to look at for just a moment. So we see that the fugacity here is pressure corrected by the factor, in this case exponential of BP over RT. Now in almost all situations B is a negative value, so we see that that exponential is going to be something less than 1. So we see, yeah, the fugacity is somewhat less than the pressure, as we anticipated, to accommodate the fact that we have a net attraction between molecules in a real gas as opposed to an ideal gas state. So it's important that we're clear about this. Well, this is somewhat limited in that it's limited to the validity of the Pitzer equation, but it gives us the idea. And you can see if I had the integrals formulated in different ways to accept pressure explicit equations of state, I might be able to get a better result, but this is going to be good enough for us to see it. Now, we should also be able to get this out of our well, V, again, just as a reminder, comes from, we have extensive database for that. Often this is expressed in an exponential form for its dependence on temperature. Or we can estimate it. How can we estimate it in terms of reduced properties? We have the Abbott correlations, right? So we can be from direct database or estimated. For example, from Abbott, and we call it B is equal to RTC over PC times my capital script B0 plus omega capital B1, and we have these guys. B0 is 0.083 minus 0.422 over reduced temperature with an exponent of 1.6. And B1 is 0.139 minus 0.172 TR with an exponent of 4.2. We've seen this before, so you've got that. But that's our access to B, so if we have that in one form or another, we should be able to evaluate the fugacity. We should also be able to get it directly out of tables, the Lee and Kessler tables. So what we see is that RT log of fugacity coefficient for some component. Rewriting what I have above. But I can get these departures from Lee and Kessler tables. But they have actually done the work for us. Write out here log of V equal to lots of writing here. Seems to me there should be a T there. And I'm not going to write the whole thing out. Same expression. But what this amounts to is being equal to logarithm of V0 plus omega. I'm going to write it in a slightly different way here. Now, actually what they've done, for reasons I'm not sure, they've used common logs instead of natural logs. So we write this equivalently as log V0 plus omega log to the base 10 V1. So if I have those values, I can evaluate V directly here. That's just equal to V0 times V1 with an exponent of omega. Now we have our tables of log V0 and log V1, Lee and Kessler tables. So I think I've got it here somewhere. So here you see what we have in the appendix of your text. Here I've got log V0, and here log V1. I've just clicked some of it so you can get an idea, and it's with the same grid. That is in terms of values of reduced temperature and reduced pressure across the top. So we should be able to get at those directly. So if I can evaluate those logarithms, then I can evaluate these. Back to where I was. I should be able to evaluate these separate coefficients, and I'm in business.
Do we have to account for the fact that we're using log base 10 instead of the natural log? Because we derived it for the natural log. So does it somehow change the value if we use?
Really.
Not really. Okay.
It doesn't change this.
Yeah, I mean, we got it in terms
Well,
of.
you have to realize
yeah.
that the tabulated values are common log, so you take 10 to that to
Yeah.
get to the value for phi itself.
That makes sense. Okay,
Yeah.
cool.
So I think I got time here to do a quick example.
Nope, you don't.
Maybe not. So let's ask ourselves to determine F or NO gas at its critical point. That's going to make things simple because TR is equal to 1, PR is equal to 1, and if we look up at the table, we'll see that the eccentric factor is equal to 0.607 for this gas. So if I go back to my table and pick off the values here, I'm going to be interested in 1 and 1 over here. So if I go over, looks like I've got minus 0.176 here for my log of P0. And if I do the same here for P1, I get 1 and 1. See if I can. Looks like minus 0.031. So log of P0 is equal to minus 0.176.
Oh, shit.
P0 itself, 0.667. Just took 10 to that power. Log of P1 was equal to minus 0.031. P1 turns out to be 0.931. So the fugacity coefficient itself turns out to be 0.639. So F is going to be equal to whatever the pressure was, right? That's my fugacity coefficient. The pressure is whatever the critical pressure was. Didn't write that down explicitly, but it's 64.85 bars. Fugacity coefficient is 0.639. Giving me 41.4 bar. Okay, so we'll go on with this tomorrow, looking at the fugacity of a component in a gas